ever forget that sound travels a mile a second. Okay? So that means in 1 second, sound can travel in the tissue and return from a depth of 77,000 centimeters, right? Because that's
Halfway.
that's half of the speed of sound. So that means that half of that means that sound can go and come back. Do you mind cutting the air conditioning back on for me? Okay. We're good with that, guys? We understand that? That's why we're 1540 meters per second, or 454,000 centimeters per second. If we have that, then that means that sound can travel to a reflector and come back at a depth of 77,000 centimeters. We good there, finance? Because basically, sound travels at 154,000. If we convert those numbers, 1540 meters per second is equivalent to 154,000 centimeters per second. If we just, from meters to get to centimeters, we're just gonna move the decimal 2 times, right? Boom, boom. That's how we get 154,000. Because remember on our steps. Because that's half of the time, that's half of the speed of sound. So this is saying that sound can travel to a tissue and return from that in at a depth of 77,000 centimeters. Okay, because that's how fast sound is traveling. So at that depth, in 1 second, sound can travel boom, boom, and back. All right. So that's also saying that sound can travel a depth of 77 centimeters 1,000 times in 1 second. Right? We good there, guys? Get that? I'll give it. Or to and from a depth of 7.7 centimeters, which is more realistic to us, a total of 10,000 times. Right? Because we already established that in 1 second, sound can travel at at a depth of 77,000 centimeters. So regardless of, no matter how we change that number, whether it be it travels 1,000 times, 10 times 77, will still give us 77,000 centimeters per second. Okay? It can travel to a reflector and back.
Can you go back 1 slide? So in 1 second, sound can travel 77,000
centimeters.
But in the same time,
there and back. It's a count for a time of flight, a go and a return time. A go and a return time. Because sound is traveling at 154,000 centimeters per second, which is equivalent to 1540 meters per second.
So it's half.
Right, because
the beginning
because that
to the end is 77, and then coming back.
So it's traveling 77,000 centimeters total in 1 second, there and back, which is why we're dividing by 2, because sound normally travels 1540 meters per second in a straight line. Okay, but if we wanted to go to a structure and come back, we can say that sound is traveling set at 154,000 centimeters per second. Divide that by 2, because we want it to go and return. Then we know that sound can go 77,000 centimeters deep and come back in 1 second, because that's half of the 154,000.
Right.
That's our thing right here. Our first equation, basically. Okay. We're good there, guys? Should I explain another way?
If you do it mathematically, you can just
That's
say
fine.
no math.
That's fine if you want to do it that way. However you understand it, I like it.
Easier.
I like it, but I know how you are, Mrs. Seal. You take stuff to the nth, perspective. I'm trying to keep us up here because this is not college physics. We're not trying to, break it down that deep. Because this is more logical, right? We already know that sound is traveling at 1.54 kilometers per second, 1540 meters per second. 1540 meters per second is equivalent to 154,000 centimeters per second, correct? Okay. So basically, that means that's sound traveling in one direction. Sound can travel there and back at a depth of 77,000 centimeters, because that's going to be half of the speed of sound.
Yeah.
Okay. Just like, again, that means sound can travel from a depth of 77 centimeters there and back 1,000 times, because that's still gonna equal 77,000 centimeters per second, there and back. Okay. Also, that means sound can travel at 7.7 centimeters 10,000 times in 1 second, because 7.7 times 10,000 is still going to be 77,000 centimeters per second. Okay. So no matter how you try to, you can math your way if you want to. That's fine. However you want to, figure out that equation. You know.
I think our mind will be tired before we get all the conception, but in math it's easier
For you.
me.
For you, right?
For me, yeah.
Everybody don't want to learn math that way. Again, if you understand it that way, that's great. If somebody asks you for your help, definitely help that person. Help that person. Right now, I want you to memorize this right here.
When it says to and from, so it's counting both directions, go and come back.
Absolutely. Absolutely. Because when we're talking about the speed of sound, we're only talking about it in one direction. We're not talking about it going and coming back. That's why we're.
This chapter both.
Yeah, because we're talking about how deep a reflector is, how fast the sound, how deep a reflector is based on how the speed of sound. Okay. So however fast it comes back, that's how we know the machine is assuming that it's at a certain depth, because the machine always assumes that sound is traveling at 1540 meters per second or 154,000 centimeters per second.
So, for the return, when the wave return, we assume that's in the same speed, but actually it is not in the same speed.
Yeah, it is. It's sound. Sound traveling through soft tissue is going to, no matter what it is, and soft tissue is going to travel at the same speed regardless. 1540 meters per second.
But there is attenuation and.
We're talking about speed, not the weakening of intensity. You're talking about intensity. We're talking about propagation speed. Sound traveling in soft tissue. Remember I told you guys this. Attenuation is different than propagation speed. Propagation speed is simply how fast sound is traveling in the media. Attenuation is how the weakening of sound as it travels.
Yeah.
The intensity of that sound weakens as it travels, not the speed of it.
But the speed is fixed.
Because it's soft tissue.
Yeah.
It's soft tissue. It's always going to travel at that speed.
And the convert to heat some. This is
That's
also.
how you're getting too deep. Let's keep it moving.
Yeah. Okay.
77,000 may be a single round trip, again, or it can be divided into many thousands of round trips, like we have right here, many thousands of round trips, 7.7 centimeters, a total of 10,000 times in 1 second. Okay. Ooh. So, and just think about how our PRP is related to our time of flight. Remember I said they're equivalent, right? So, using this formula right here, guys, PRF is equivalent to 77,000 centimeters per second divided by the depth of the imaging depth. Okay, so we can actually determine our maximum imaging depth based on this formula right here. So they may even ask you, what's the maximum PRF of, a depth of 5, then we know to get our maximum post-repetition frequency, we have to take our 77,000 centimeters per second divided by 5. Okay, so I do have a couple examples right here, guys. All right, because basically even though it's changing the actual units, right? It's changing the actual units. That's like I can say sound is traveling at 707. I can use 770 meters per second as well, right? It's going to be the same thing. If I'm taking it from centimeters to back to meters, right? I can still say 770 meters per second divided by the imaging depth, which is also going to be our inverse relationship to the PRP. Okay, because our PRP is the depth times the 13 microsecond rule. This is the 77,000 centimeters per second, or 770 meters per second divided by the imaging depth. Okay. So with a depth of view of 7.7, it's giving you these numbers because we want it to be easy math. Okay? If we need a calculator for the exam, I have them now. Okay? So when the depth is set to 7.7 centimeters, we already kind of answered this question because we had this on the last slide. 77,000 divided by 7.7 is gonna give us, who got the calculators out? Who can give me the answer before I show it?
10,000?
Somebody ask Siri.
No,
My
let's do,
man.
let's do the
Huh.
My
calculation.
man, that's what I'm talking about right there. That's what I'm talking about right there. So our pulse repetition frequency is gonna be 10,000 hertz. Guys, these are formulas right here. You do have to know these formulas. Okay. You do have to know these formulas. Remember I said like maybe what's a formula? The IRC, the ITC. I said just recognize them. This formulas right here, you have to know these formulas because the test is gonna ask you to calculate these. Okay. So know these formulas right here. The ITC and IRC, like I said, just be able to recognize them. You don't have to apply them. These, you have to apply them. Right? So when the depth of view is set to 15.4 centimeters, what is our PRF?
20.
No calculation.
You doing long division?
I can do it, yeah.
You on your phone all day. You ain't gonna pull your phone out for this?
No.
Lord have mercy.
Oh, because
Somebody give me this answer. This is gonna take Uber all day.
It's
I'm
not.
down.
Why
Let's
you
go.
saying that?
PRF is because I need the answer quick. I don't want you to be sitting up there this like you in trigonometry trying to figure cosine. We don't need all that. We just need the calculation. Use the calculator. Okay?
Okay.
That's gonna be PRF is gonna be 5,000 hertz. Or that's also saying that it's sending out 5,000 pulses per second, correct? Right? Okay. So again, guys, know these formulas. Know these three formulas. Alright? Ooh. So we have our question right here. I should have made those answers pop up so they weren't on there automatically. These answers are already the question in the back of the book. See, I'm force feeding it down your throats now because I know when I say it, everybody will read them. But hopefully you remember these answers. Okay? So a sound wave is created by a transducer, reflects off an object, and returns to the transducer. The depth of the reflector is 10 centimeters in soft tissue. What is the go and return time? Okay?
1,300.
So we know it's 10 centimeters. We already answered this earlier in the lecture. 10 centimeters multiplied by 13 microseconds per centimeter is going to give us 130 microseconds. Okay? That is going to be the go and return time. Okay? What is the total distance traveled?
20 centimeters.
20 centimeters. Thank you, Dewey, for my unit. 20 centimeters. So I'm saying that because just like I changed the question last time on the last test from IRC to ITC. You know, I can change this one as well. So just be careful about what I'm asking you for. Okay? All right. Do the second one. Okay? A sound wave is created by a transducer, reflects off an object, and returns to the transducer. The go and return time is 26 microseconds. What is the depth of the reflector? Using a 13. So the way they have it in the book, they use this 2 times 13 microseconds equals 26. But you can also just divide that number, right? By the 13 microsecond. So 26 microseconds divided by 13 microseconds per centimeter equals 2 centimeters. Okay. We're good there, guys?
Yep.
We're golden? It is. It's telling you, remember our 13 microsecond rule says that every 13 microseconds, sound is traveling 1 centimeter to speed. Okay? So if it goes 26, if our go and return time, because remember our 13 microsecond rule applies to our go and return time or our time of flight. Okay? If it goes 26 microseconds, that means 13 times 2 or 26 divided by 13 will give you the depth of that reflector, which is 2 centimeters. Total travel time would be 4 centimeters. All right. Ooh. So, a sound wave, because I'm just doubling, when I'm talking about the total distance traveled, I'm just doubling the depth of that reflector. Okay. So, a sound wave is created by a transducer, reflects off an object, and returns to the transducer. The go and return time is 26 microseconds. What is the total distance traveled? We just said that answer.
4
We just said that answer. It's gonna be 4 centimeters, right? 26 microseconds, I go and return. The depth of that reflector would be 2 centimeters. to get our total distance travel, we're gonna take
Times
the
two.
depth of our reflector times 2, and then we're gonna get 4 centimeters. What I'm asking for, the total distance that pulse traveled, there and back. Now let me know if we haven't had time getting this.